very conducive to the discussion later. And I have about 4 or 5 discussion or question for the people to work together. And the question style will be like you kind of select a group of 4 or 3 people, and then you will select groups to come present the answer like after the discussion. So be prepared about that because that will happen. And if the faculty want to join, it's okay too. It's actually going to be great if the faculty want to present their own answers and let everyone else like judge. But we only pick one answer at a time, so we don't have everyone coming up because we don't have that much time. So I'm going to talk about from machine learning to deep learning. I think I read the application of the students. A lot of you have done a lot of work. So I'm not going to tell you how to write the first convolutional neural net on Keras or PyTorch because you already know. And I think I want to do a quick survey at the beginning. So how many people have no idea of how to write either PyTorch, Keras, or TensorFlow, or any of that sorts on a simple convolutional neural net? Oh, wow. OK, so like 0 idea. So other than faculties, which is OK. We don't have to worry about them. How many people who are in the program who don't know how to do this? OK, so I might actually touch on this a tiny bit. And the other thing is that I actually have made lecture notes just for that. And I can just put it as a PDF. And that will be probably most useful, I think. Because otherwise, we'll have 2/3 of the people who would be like sitting there and just basically going on the Instagram account. So I know, I was sitting in the back. Come on. So the lecture is based largely on the deep learning book by, for those who don't know, Ian Goodfellow, Joshua Banjo, and Anna Caulfield. And they're excellent. And I actually learned a lot from this book. And it's completely free. So you can download it 100% free as a PDF. It's like $30 on Amazon if you can afford it. And ideas also drawn from Stephen Millar's deep learning lectures. I found most of the materials online are very engineering driven. So like if you look online, they basically teach you everything you need to know to make a neural net work. These are the stuff that you tune, these are the stuff you change. But none of them actually provide such an in-depth sort of like ideas why it is this way. So I think this book is actually one of the best if you haven't actually read a book before about deep learning. And it's free. So quick introduction of myself and what I do. I just want to quickly run through what I do, and I want you to know what I know, because I don't know everything. And for the first lecture will be sort of introduction to deep learning, mostly like ConvNet style stuff, and why it is important, certain ideas that we draw from the traditional machine learning. The second lecture and the third lecture, I'm still pulling materials together, but the second lecture is likely to just be like recurrent neural nets and maybe RIM, recurrent inference machine. But if there's other suggestions, you should tell me. I can also do reinforcement learning. That's another possibility. The third lecture, I was thinking about looking at something called CapsuleNet. So Jeff Hinton, basically the godfather of machine learning, recently came up with something called CapsuleNet, which supposedly deal with some serious problems in convolutional neural nets. And so I was going to talk about that. And then the other thing I was going to talk about is the popular thing that's recent, very hit in the recent NIPS and ICML is all graph network. So if there's other suggestions, feel free to talk to me during the breaks. And I'll be happy to change my lectures because I have a bunch of materials. So just let me know, OK? So what I do, this is my first foray into deep learning. I've done machine learning before that. But this is like before there was 3D convolutional net. They were having 2D convolutional net back in 2016. We have an ICML paper that we looked at. Can we just go from like cosmological simulations to cosmological parameters with a ConvNet? And we had the first effort to actually make a 3D convolutional net back then. So that's the ICML paper. We realized that I achieved higher accuracies than a traditional method. Sai McGrenna is a machine learning faculty at UBC, actually. So the ground truth versus prediction, you can see that it actually shrunk quite a bit compared to our traditional method, which is the red dot, which is what I got sort of tenure for. And the other thing we recently did that just came out with some press release recently is how to use deep learning to simulate the whole universe, the whole freaking universe. This is just the gravity part of it. It was published in the Proceedings of the National Academy of Sciences. We went from analytical approximation, feed it through something called a unit, and then we would output some predictions of the full numerical simulation. So going from a 3D analytical approximation of the universe to the full phase-space distribution of all the particles in the box. So that's what the machine learning did. The deep learning did, we used basically UNet, which is very, very simple. It's 60 million times faster than the simulation that we usually run. It's not as exactly correct, But if you look at something called the Pell spectrum, I'm assuming this is astrophysics crowd, so I'm not going to explain this, what a Pell spectrum is exactly, but it's the Fourier transform of the correlation function. As a function of scale, the Pell spectrum, the truth is the green, which is the simulation, and you can see that the machine learning prediction, which is this unit, is basically impossible to see under the green line. Oh, thank you. There's a technology that I don't use, physical technology. And the other analytical approximation scheme is right here, and you can see it peaks out tiny bit at k goes to 0.7, which is when you start having other effects like gas hydrodynamics that come in. So we thought that was kind of cool. The cool part of this is not that it's just really fast, because you need to produce a training set if you make it really fast. It also extrapolates. Extrapolates not within the original distribution of the training set. For those who don't know what I just said, there is the idea that you have the training set that you train the machine learning algorithm with, and if you put a test set that's actually different from the training set, different in the sense it's not drawn from even the basic underlying distribution, but it's actually completely independently different. You extrapolate. Can it do it? And it does. And that's why it's surprising, and that's why it was on this PNAS paper, where we input omega matter universes of omega matter of the universe 0.1 and 0.5, while the training set's all 30% dark matter universe. And it extrapolates so well, you can see that the long dashed line is basically just peaking out from 1. So 1 is good. That basically describes the error Pell spectrum, and it also encodes information of phase correlations. We also did extremely well. So what happened? We didn't overlap the training set with the test sets. We did not explicitly use any transfer learning or meta learning. For those who know the field of meta learning and transfer learning, maybe there's an overlap information somewhere between these universes, where it's 10% dark matter, 50%. We also tested 90% dark matter, by the way. Maybe universe is fairly simple, so that generalization is and extrapolation by network is easy. There's a lot of work that we work with people like Stefan Millar to try to understand why a network works to extrapolate outside training set inherent distribution. So we don't know the answer though. Can we explain or interpret this generalization? It's totally work in progress, but I will talk about this work for like 20 minutes tomorrow. Other cool things that we've been doing, we also use deep machine learning to learn the hydro plus gravity. Before, I only used gravity for 60 phase space informations. Now it's like we go from gravity only, dark matter plus dark energy, which is what we had before, to including hydrodynamics, and baryons, which is basically learning from something called the Illustris hydrodynamic simulations. These simulations are very, very expensive to run. This is how well we're doing. We basically have a target, which is the green line. It's a Pell spectrum of the galaxy as a function of scale. Benchmark is the orange line, which is the HOD model that we tuned. It's actually not bad. Notice, this is 10 to 0. This is k equals to 1. So HOD works perfectly well, down to k goes to 1. It's just starting to not work well at some point here, about k goes to 1. And our method works really well all the way down to k equals to a few tenths. So that was pretty interesting. I took some of my slides from the DeepMind talk I recently gave, so don't mind the DeepMind question here. So we thought that this is interesting because our method, which is inception plus R2UNet, which is very, very simple, it's a two-phase neural net, works so much better than the state-of-art HOD. On the other hand, it's not too surprising because HOD, you only cannot get the galaxy scale correct. And the training simulation takes about 100 million CPU hours, and our whole process of training plus prediction takes 3 hours. So that was a bit fast, even including training. So we also use GANs, so I also understand GANs quite well, although nobody understands GANs. Don't trust them when they say they understand GANs, so don't trust me. We tried probably over 20 different GANs to get this project to work. And each GAN's stuff that we actually tune like so many parameters is crazy. The training set is 100 million CPU hours, the same Illustris simulations. We want to get the neutral hydrogen distribution, something that Jason actually mentioned a lot today. You did STEM Lamanava forest, it's all neutral hydrogen. Our prediction talks about 2 seconds, and the results increase across 9 orders of magnitude, from very low density region to extremely high density region. And if you look at these two sets of simulations, I actually don't know which one is the truth, which one is the generated ones myself, like I can't tell. There's another plot that's more quantitative. Here's a scaled effective mass of neutral hydrogen as the PDF. And the benchmark here is the HOD model by Francisco Navarro Velasqueza, which is like recent HOD model. And you can see that the benchmark is so far away from the target and the prediction. While it works really well, when you have basically sort of galaxy-like neutral hydrogen. So it works well from all the Dam Lyman alpha forest system and the Lyman alpha forest, Dam alpha system, sorry. So what we've done so far in our group, we have an analytical approximation of the universe, which is gravity only, to full ML simulations that usually takes 1.8 million CPU seconds. And then these are 100 million CPU hours. This is Illustris that goes to galaxies or gas and other, galaxy properties and other things. And what we did recently is to turn it into 0.03 seconds to do this, and 1 second to do that, and 2 seconds to do that for predictions. This part extrapolates really well, so it's extremely useful. These parts we cannot test whether they extrapolate well yet because we only have one Illustris simulation to train. By the way, don't never let people tell you that, given how little data you have, you cannot use machine learning. I mean, this is one simulation. And if your one set of data is so complex, it has a lot of information in it, it is still possible. So there's some, ideas that people say, well, cannot never work with astronomy because you only have one universe. But the universe is complex. It has a lot of information. The complexity itself actually gives you a lot of power here. So, okay, so that's what I've worked on. So it's mostly convolutional neural nets with different dimensions and different styles and GANs. So I'm learning, my students are working on graph neural net these days, so I know a lot about graph neural net because of that. And CapsuleNet I'm just learning, and I also have reinforcement learning projects going on. So that's my background. So feel free to ask me questions during the break. I'll be here for 2 days. So outline today, quick survey. So we just did the quick survey. There's like a few people who don't know anything about convolutional neural net, but majority of it, I remember, have quite a lot of experience on this one. We have to form discussion groups. Do you have friends yet after being here for a few hours with the people next to you? So just think about, we'll be asking you to form discussion groups within around you, so you'll be discussing. So think about who you're gonna talk to. So I'll suggest 4 to 3 people to form groups together so you can actually check. Just can you do that right now quickly? Just know who you'll be talking to when you All right. I wish I have a gong here. Bang. All right, introduction then. You have some group. Who doesn't have a group? All right, everyone's good? All right, we'll have discussions later, okay? If you don't have a working knowledge of one of these, TensorFlow, PyTorch, or Keras, please set it up tonight or today. Even for old people like me, it takes only a couple hours. So you should be able to do it much faster than that. All right, cool. Lecture today, we'll do broad overview of machine learning. I found it really, really useful. I surprised myself that I found it useful because I thought I know how to do this simple convolutional neural net. I know how to do this graph network. I should not need the introduction. I found myself learning something new even when I just read the introduction because I think, if you don't know who Joshua Bengio is, he knows this stuff from way back in the beginning. And Ian Goodfellow did a really good, overview of why things work this way. And a lot of people don't know this. If you just take lectures online, it's very engineering-like, and they don't tell you why certain things is the way it is. So I think it's good to have that. Deep learning intro, this is just gonna be convolutional net. Lecture tomorrow, RNN, RIM for the first one, and GraphNet and CapsuleNet, and possibly reinforcement learning for the second one. It's gonna be going fast, but I think a lot of them actually, and you will have to work on project to actually understand it, but I'll just give you a sort of overview. All right, let's do that. Well, I hope you'll get out today a bit of history and development of ML so you know what ideas to tap into when you run into research questions. Some of these are useful for your research, I think, and I learned it myself. Several concepts of ML that are useful for current day deep learning, not just for historical reason. Representation learning, overfitting, underfitting, capacity of the network, how you change your network, not just tuning like any number of parameters, because there are a lot of them. The performance, and how will performance change as you change the capacity of the network? How do you overfitting, underfitting? What makes traditional machine learning work? And think of why deep learning is different from the previous generation ML. Or flip it away, why don't we use the old machine learning method or the old statistical method or just methods we know that we understand in comparison to deep learning? And reverse CNN in your head. So I hope this is what you'll get out today from the lecture. That's my goal. But if it doesn't work, you let me know, because I don't sleep very much last night. So, and raise questions anytime. It's all good. I'm not too scary, I hope. I have the idea that if you're not too scary, people will ask you questions. If you don't ask me questions, I'm assuming I'm a bit too intimidating, and I'll be very sad and crying at night. All right? Sounds good. Okay, good. This is ready? Let's go. So overview of ML. This is a little bit traditional, but I think people want to ask. When programmers program computers, this first conceived, Ada Lovelace in 1842, like way before anyone was born here, I'm assuming. Over 100 years ago, before computers were even built, they were asking whether machines can become intelligent. In early days of AI, the field tracked problems that are very easily solvable by computers, but very difficult by humans, such as chess. These have rules. These have well-written rules. The true challenge, however, to AI might be to solve tasks that are easy for people to perform, but hard for people to describe formally. So there are no rules, basically. One solution to this challenge is to allow the computer to learn from experience and understand the world in a hierarchy of concepts. This hierarchy of concept actually comes up through what is this deep learning part, and defining relationship to other deep, simpler concepts. So if we draw a graph to represent how concepts are built on each other, the graph is steep, and that's why people start thinking about this graph and with many layers, and that's why they call it deep learning. That's what people originally think about deep learning, at least. Then many other people will say it differently. Many early success actually happened in relatively formal and very sterile environments, and this is actually a fun example. And they require computers have a lot of knowledge about the world. Like chess, they actually win pretty well. Person's everyday life, however, requires immense amount of knowledge about the world. And computers need to capture this in order to behave in intelligent ways. So hard coding of knowledge in everyday life is difficult. There's an inference engine people use to try this. They write all the rules and then try to make the computer figure out what's going to happen. But it failed to understand how a person shaves in the morning. Because when Fred uses electrical shaver to shave, it asks whether Fred is still a person, because the electrical part here and Fred, which is a person's name. And this inference engine has completely failed if all the rules, they just hearken to all the rules of everyday life. Cannot figure out Fred is a person or not, because there's electrical and there's a person. Is this person electrical or not? And so that's the failure of the early day machine learning. And so this suggests AI needs the capability to acquire knowledge from raw data, just directly, without us telling them the rules. And that's what machine learning is about. Features of representation learning. This is something that people really understand here, because there's Cartesian coordinates and polar coordinates. The performance of early machine learning algorithm depends heavily what representation you give it. And the algorithm only learn the correlations between the features and the outputs, and you cannot change the features. The algorithm does not change any of the features. And I think the idea is that dependence of representation is a general phenomena in computer science everyday life. Like, we need the representation to be correct. However, many tasks, it's very difficult to describe exactly what the features should be. In image processing, we look at edges. So when you look at ReLU, it's basically just an edge function at some level, right? You zero, or you do this linear function. Other versions of ReLU is the same. Other version of activation. It helps you to find edges. But say in astrophysics, you need to find all the spiral galaxies through images. Want to use presence of spiral arms as a feature. But if you just have the edge, you might not figure out, just like a piece of the edge, you might not be able to figure out that's a spiral arm. So if you just tell the machine what the representation should be looking at, it's not so trivial. So one solution for this problem is that use machine learning not to discover not just the mapping for representation to output. Remember the correlation between the representation to output, but also the representation itself. So that's a whole field of representation learning. So autoencoder, for people who hear about autoencoder over and over again, is basically a combination of encoder function that converts input data to a different representation. So this bottleneck. They also talk about bottleneck theory. They have many names of the same thing. That converts basically all this like large representation, large data set into like a smaller, crisper representation that's better, and then you convert it back to original format, but original format with better properties. So they're trying to preserve as much information as possible, while when you run it through the decoder, it also makes a new representation that have nice properties and make it expand back. That's very similar to also to UNet. So all these concepts connect. Autocad encoder has been around forever, right? And the idea of representation learning is not new. Like you want to use polar coordinates sometimes and Cartesian coordinates another time. So I just want to make all these connections back for everybody. So why deep learning? When designing features or algorithms for learning features, you usually want to separate the forces of variation. So like what things are changing what. You've seen this picture a lot. This is Ian Goodfellow, famous paper 2014. He's trying to look at these pictures of this image. Back in 2014, those are the images people look at when they look at, GANs or, CNNs. They look at the visible layers, and you look at the hidden layer, and you find out that a lot of it is not making any sense, but some of it is like edges, or they have colors of different types, and that's how they decide whether this is a car, a person, or animal. That's what all these inside layers were doing. So for coming back to astrophysics, the appearance of galaxy in this energy distribution will probably depend on the age of galaxy, when it last merged, when is the last major merger, is there a black hole in the middle? But all these stuff are not directly observable. So it's hard to design this representation a priori by ourselves. So all these factors of variation influence every single piece of the data that you feed it in. But then it's nearly difficult to obtain this representation because these might not even seem to help us because you don't even know what the representation should be sometimes. Should I put in the age? Should I put in, when the last major merger happened? But like how would it affect what we see in the data is very difficult. So deep learning directly solves this problem by basically introducing representations that express in terms of other simpler representations. And that's why the deep part. That's why building these deep graphs allows computers to build complex concepts of simpler concepts. So when you think about all this multiple layer, some people like to think about, if you're physicists, like to think about it as sort of like a multi-scale, because every single layer you have probably different future sizes, and there's all this information coming back together because they probably correlate across scales and feed it back together up to the top. To the last output. Does that make some sense? Okay. So an example deep learning model, multi-layer perceptron, the simplest one, is a mathematical function that basically maps some set of input values to output value. The function is formed by composing many, many simpler functions. And that's the idea of the simpler concepts, hierarchical, and that's why the deep part. We're going to think of each application as a different mathematical function as providing new representation of the inputs. So quick question with the people in the group. We'll spend about 5 minutes, maybe not even 10 minutes. How is representation learning related to scientific problems that we try to solve every day? I have some paper discussion that I can show you guys if you like, but I would like to see people sort of discuss a little bit. Yeah, let's start. Let's do 5 minutes first, and I'll show you what the papers I wanted you guys to take a look. And I will pick a group to talk about it at the end. Dun, dun, dun. You won't get repeatedly picked, or you can volunteer. Hey everyone. Here are the two papers that might be interesting to lead to more discussion for about 3 more minutes. And then we'll come back to have one group to tell us about what they think. If you haven't seen those papers, I picked those two just because it's about representation and science. The first one is distilling physical law using neural nets. It's a science paper back in the days before neural net is what you know as neural nets. The second paper is a more recent paper about how they learn what halo formation depends on certain things. They don't even use deep learning. They actually use gradient boosted trees. All right, we have 3 more minutes, and then just take a quick look, and then we'll pick a group, or someone will volunteer the group to tell us something, what they think. Thanks. Go back to discussion. All right. I know people can read these two papers for a while because they're quite interesting. I got one group that I forced volunteer them to tell us what they think about the answers, and you got like 1 minute. Want to tell us? You can just sit there if you don't want to come out. is great. I mean, I'm just hoping this will be how it works for next 3 lectures, if that's okay with everybody. And applause for those who came first. All right, let's move on. We can't go through all the groups. Anything about graph network? Okay, it seems like there's enough people who don't know about graph network. We'll probably not discuss it too much further, but we'll do the lecture. The third lecture will be on it, partially at least. So just for those who know or heard about graph network and deep R, are the two things everyone wants to do right now as of the last ICML. So there's a reason why I brought this up. But this has, graph network has been around for, it's been around for a while. And people haven't really used it until recently, so successfully at least. So for example, Peter Battaglia's work, they were able to make predictions of robots, like how robotic things move by using graph network, by modeling all the components of the arms and the legs separately as different components and modeling the forces between them. So that's like one application that's very widely adopted. They can also talk about how to build houses in a way that's most efficient. That's also using graph network. So there are some examples here. I'm not going to make the group present because I realize we probably should do this on the third lecture. All right, that sounds good. All right, we'll go back to the lecture in 1 minute. I think someone just ran to the bathroom. But so graph network, if you guys are interested, pull it out tonight, and I'll be happy to talk more about what people are using it for. Definitely tomorrow on the third lecture. And if there's any other suggestions what we should include, let me know during the break and lunch, okay? Thanks. So people coming back, I'll start the lecture again. How are people doing? Are you tired? Should we have a break, or are you okay? Okay? No breaks. That's just these people saying, not me. Okay? Yeah? All right.
Do you have a reference for the house building machine?
It's a recent ICML paper. I need to look it up. I would look it up and put it on a Google Drive tonight. So is another lecture said that's how to build CNN, like simple CNN. I will also put it up on the whatever Google Drive that you guys have.
Me and I'll
You'll put it somewhere.
Yeah.
Okay. All right, hopefully this works. Everyone's back, okay, more or less.
Please work it out.
I touched. Oh. This is an engineering problem, not software engineering. Let me try that again without touching the screen, any other connection. My USB-C connector is slightly off, so that's why.
I have another one.
Yeah? Maybe it's coming up, maybe it's coming up.
Sticking. Yep.
Yep, all good, thank you. All right, we're lucky. Or you're not so lucky to have me for another 20-ish minutes. All right, so neural networks, 1990s to 2000. At this point, many believe deep networks are completely difficult to train. But these three people kept neural net alive, so-called. I think at their work dinner, they were discussing how some of them were having trouble getting tenure. So this is how bad it was. But they all got tenure in the end. Neural net circa 2006, Hinton 2016 showed deep belief network can be trained with greedy layerized pre-training. It was like the first thing that started. Joshua Bengio and Rensado showed similar methods can be used to train other deep network. And all of a sudden, deep network actually outperformed very competing AI systems. The most recent ones that you probably have heard of is work like, they beat the best Go champion in the world, or the protein folding work that I'll probably briefly touched on, that they actually also beat the best, all the teams in the world in predicting what the protein shape should be. So all these things had happened recently. So let's do some basic of machine learning. What is learning? We're not going to do the discussion because I think we don't have that much time. But what is learning? I mean, this is something that you should ask yourself. What is machine learning? What's learning exactly? Tom Mitchell, who was the machine learning department chair in Carnegie Mellon until recently, asked the same question, and he defined it in this way. A computer program is said to learn from experience Y with respect to some class of task T and performance measure P. If its performance at task T is measured by performance P improves with more experience, then it's learning. Okay, so that's very abstract, the way and it's very hard to read and speak. But it's very simple. It's like if you can improve your performance at this task with more experience, then you're learning. So that was the definition. People have come up with other definitions, but Tom Mitchell's definition, I think, sort of survived all the other ones. And what are the common tasks done by machine learning these days? Classification, you actually talked about image classification earlier for astrophysics. Classification with missing inputs. So this is a little less often in astrophysics. If you have, a group of data where you have missing inputs, like what do? There's also people who look at something called in-painting. They will talk about something called in-painting or deep image prior, if you haven't heard of these things, where they took pictures of the library, and then they take pictures of many libraries, and then they're able to in-paint a picture where a significant fraction of the library is basically empty. But you just can't see that part of the image. And they were able to in-paint very well. That was called deep image prior. That was a paper if you want to look it up. Regression, I show you the work where we regress to cosmological parameters. He also mentioned his work on mass maps to cosmological parameters. There's a lot of regression problems in astrophysics. I personally think not all regression problems should be done with deep learning. My goal is, if you can use traditional method to do really well, don't use deep learning, because it's really hard to understand what you're getting sometimes. And that process, understanding why it works, is probably sometimes its own research project. Structure outputs. So output is a data structure that contains important relationship between different elements. So what does that really mean by structure outputs? NLP, based natural language processing, is a good example. Machine translation or transcription, where you have unstructured representation data like discrete textual form, where you go basically voice to text. So that's another example of that. Another structure output is people actually have looked at very interesting recent development, which is you can translate from multiple languages to multiple languages, not just one-to-one, which is an interesting, I think, probably one of the most phenomenal NLP breakthrough recently. If you've never heard of it, it's called hypernetwork. You can Google it. It's this hypernetwork. It goes from any languages to any languages. And how it works is that it takes a network to do the translation, but it's trained by another network. So the another network will actually know which type of network to run and which type of model they should use by tuning one another. And that's, I thought, really quite interesting. I mean, it's not a crazy idea to use one network to train another network, but the fact that it works for multiple language translation is quite interesting. Synthesis and sampling. We have speech inputs, but we want a large number of possible outputs of spoken version of the same sentence. Different language outputs. Imputation mixing values. This is the in-painting that I mentioned earlier. Denoising. How many people have thought about using denoising on astronomical data set? I thought that was interesting. Yeah, exactly. I totally thought that was very, very interesting. The only reason I'm not doing it is because there's a lot of classified work on it. And I don't want to touch it yet. There's a huge literature that's classified that's obviously for looking down Earth. So I didn't want to compete with all the classified literature on this one. Density estimation, probability density estimation, continuous X, and probability mass function estimation, which is a discrete one. All right, so these are the common tasks. If you list and think about all the different things people are doing in machine learning, these are the tasks that we're doing. Any other suggestions of what people have been doing that we forgot to mention? All right, people are getting close to being tired. We'll see. All right. Machine learning performance measures. So accuracy. So the first thing people will probably talk about is proportion examples for which the model got it right. The error rate. The proportion example is that the model got it wrong. It's very simple. The average log probability the model assigned to some examples. And performance measures can be hard to define sometimes. For example, in translation, if you got some of the sentence right and some other relationship objects wrong, do you rate it as bad or is it good? So sometimes the performance measure is very difficult. This is a team question you should do later, is to come up with astrophysics applications for each of the general tasks we discussed. Think about what research project you could imagine doing, given the list of things that machine learning could do that we just discussed. And maybe this is a project you could do in this program for the 6 weeks. So unsupervised versus supervised learning. We have experienced a data set containing many features and then learn the useful structure of the data set. usually you learn the entire probability density distribution of that generated data set explicitly with density estimation or implicitly with denoising or synthesis. Or you can use clustering. So all these concepts are actually quite related to each other, if you haven't noticed. For the supervised, this is something that we're probably way more comfortable with at some level. We've observed examples of many of the X and associated factor, like many spiral galaxies and elliptical galaxies, and you know the spirals or ellipticals. And you can decide its probability distribution. And you can do it with Bayesian, statistics, but you can also do it with deep learning, or not. There are other things like semi-supervised learning. Some examples include a supervised target, but others do not. Multi-instance learning. Entire collection examples is labeled as containing or not containing an example of one class. Reinforcement learning, this is something quite new that interacts with the environment with feedback loop between the environment and the learning system. One example that I think we're sort of working on, I think people are working on too, is to use that for adaptive optics, right? Because you have too many little mirrors. And it's a really interesting problem because all these little mirrors can be controlled, and you have one objective goal, which is to make clearer image. And it could be a very interesting reinforcement learning because you do this and you see what happens, and you have a lot of simulations and a lot of data you can use to train. So that's one possible reinforcement learning problem. Another obvious one that we haven't quite done it, but we're looking at it, is to look at the fusion. Fusion system where you have an entire machine, and then you have all these many knobs, and you have data of what people have happened before, and also simulations of what things will happen when you increase the ion flux at this particular angle with this speed. Another reinforcement, and you have an objective goal too, to create a stable plasma that will actually be less expensive than it takes to generate the energy. Other suggestions of reinforcement learning problem? I mean, the problems I just suggested is not published, by the way. This is just ideas I'm throwing around. Yes?
We have on Galaxy Zoo at the moment messages sent to users to say, hey, thanks for your classification.
You want to say it louder, or I give you my mic?
I can just yell. We have on Galaxy Zoo messages.
All right. Any other reinforcement learning suggestions? Do you give them treats? I don't know. I mean, you give them kudos, I suspect, or like smiley faces and stuff like that. Any suggestions for other deep learning, deep reinforcement learning?
A similar one to your AO is, of course, to use, control a telescope for guiding on a star, maintain either image quality or just for spectroscopy. You've got heuristic-based models right now.
I think it would be really good. This is something we haven't actually done, but we're talking about it. And there are deep reinforcement learning experts who want to work with us from DeepMind. Flatiron is forming this connection with DeepMind where we work together on several problems. And so this is one of them that they're interested. We haven't got the right. So like we don't have a telescope access, right? So I can't just tell them, well, you should do this. Because I don't have a telescope. And they want to test their algorithm on the telescope if it works. So it'll be interesting to talk about. Maybe some students want to do it instead of me. Other people. You don't have to stand but loud so they can hear you.
Reinforcement learning for a target selection, then you will make the statistical inference become a bit tricky because your selection function is super nonlinear.
So coming from someone who's done a lot of target selection for Sloan, I agree with you that we don't want to make the selection function all that complex if you want to do clustering of the stuff afterwards. But if you want to use the laminaire force from these quasars afterwards, then it might not matter. So it depends on the problem, I agree. Other suggestions? All right. I mean, deep reinforcement learning, a lot of it is robotics and self-driving cars, the two obvious ones. All right. Cool. So how to describe the data? Right now, they usually use something called a design matrix. Each example is along the row, features of each example in the column. They sell M elements, but each element doesn't have to be all the same size. Labels can be a set too, like a whole sentence when you do the language translation. Or you mean all the galaxy properties you can think of when you want to predict in Illustris, for example. There's a linear regression example, because if you cannot understand linear regression, you cannot do deep learning for sure. It's simple. You have weight, you have features. All of these are actually very, very similar to what you've been doing for prediction of y equals to weight transpose times x. Measuring to success, you do mean square error. This is test error for those who are thinking about test and training already. Quick homework problem 1. We're going to do some of these homework problems. You don't have to do it now, but just read it. I will post the slide so you have the problem track. Set a simplified matter power spectrum P of K generated, so power spectrum of the universe, generated by CAM or class, whatever you like, plus noise. Gaussian for now, so don't put other noise in it. Can you characterize P of K as a power law with just this function? You can regress to find A, B, and C with your choice method. I've tried this with, you can do, very simple likelihood, or you can also do ConvNet. So you can do whatever you want. And it will be interesting to see what your answer compares to the other method too. So the linear regression method versus deep learning. And the answers are slightly different, just to give you a sense why I asked this problem. The answers are different, and we don't actually know exactly why. Let me give you what my answers were. If you do it with ConvNet, you'll have slightly lower error at the large scales than using linear regression method. We've tried this. We don't completely understand why. We're trying to come up with reasons why. And the other thing is, interesting research problem is if you add systematics to, say, the small scale of the power spectrum. For those people who don't do clustering, small scale means large K, which is, say, the galaxy. Astrophysics we don't understand. You add some extra powers towards the end as a training set. And can you make the neural net realize that the cosmological prime is the important part and not the gastrophysics? You can marginalize over the astrophysics part. So that's a homework problem plus. You don't have to do that, but just do this for now. Linear regression or do a ConvNet, just to practice. It should only take like 6 lines. I mean, I think it takes 1 line to generate the power spectrum. If you don't know how to run CAM or class, it's downloadable. It takes about 2 minutes to install. And I know CAM is actually very easy. I've not used class myself. Do people know how fast class install? No? Okay, so I know CAM is very, very fast, because it's a very, very old code. So it should be pretty easy. It should take about 6 lines. Should not be more if you're using like PyTorch, which I'm very familiar with. All right.
How large the data set could be?
Huh?
How large? How many power spectrum?
You should try. I mean, you can generate as much as possible. It takes like seconds to generate these power spectrum. So you can generate a lot of them. You can share with your friends, But you want to make sure that, you want to cover the basis. What is the range of A, B, and C you want to cover, right? So you can also just forget simplified power spectrum. You just generate a bunch of power laws. You can actually just generate power laws and put noise in it. That will be even simpler. You don't even download the first thing. This is for the people who know cosmology. If you don't care about cosmology, just generate a bunch of power laws, add noise on it, and just do it as a regression problem. Try it with simple linear regression, and the other one with maybe ConvNet. You don't have to do both, but just at least do one, so maybe we'll have some comparisons to see what happens tomorrow. Fun stuff for the faculty. Takes about 6 lines.
I'm asking this question because I always come to this question when I think of any problem I want to do. Because let's say, what is the, how do you decide how many samples you should have in the training? This is a hard question because let's say for the MNIST data set you have 6,000 per class. So what
This is a very simple one. You don't need a lot. Yeah. All right, so let's do that for fun for homework. I know you guys are supposed to hang out, but you're also supposed to learn a tiny bit. And you have the afternoon, so hopefully you have some time to do this. Capacity, overfitting, underfitting. So this is something very interesting because I didn't quite understand how capacity of the architecture matters so much and how underfitting, overfitting changes as you change the capacity of the network. For people who don't know this, what is capacity? Do people know about capacity of the network? Like, what does that really mean? No, okay, I see a few shaking heads. So let's back up a little bit. Generalization is the ability to perform well on previously unobserved input. But hopefully that unobserved input follows the same distribution of your training set. Okay, so that's what I'm talking about with generalization here. Machine learning needs to have low generalization error, which is the test error. People have done training errors. You train the thing, and then you want a training error to be low. Underfitting is when the model does not have low enough training error. Overfitting is when you training error and the test error is too large, like the gap between the two, which I will show you some examples here. Very simple example. This is underfitting on the left. Appropriate capacity, these are very simple points. And overfitting, you can see if you have a network that's crazy and say you can have many, many ordered polynomials, it will fit basically all the points. And you don't want that. So there's a very simple regression examples. And you can start with the linear, just second order polynomials, and 9 order polynomials. So you can see how the capacity of the network, in this case, by showing you how many, basically, is it 1 to 9 or 1 to how many? So how the degree of polynomial is the capacity network. Does that make sense? And the representation of capacity here is kind of interesting. This capacity model can be changed by changing number of input features or adding new parameters associated with the features. There are many other ways changing capacity of the model. So finding the best function within a family of functions the model is allowed to have is a difficult optimization problem. In practice, we find a function that makes the training error small enough. That's called effective capacity. And quick question to think about this is, what are the other ways to change the capacity of the model? And think of the problems that you've thought about before. For me, I will think about, how many layers or like what's the filter sizes. That might change how the capacity model change, for example. My experience coming from, say, look at a cube of the universe. And if you change different layers, the number of layers, you will actually increase or decrease the capacity of the model significantly. And how big your filters are will also change what information from which scales you're getting from. Does that make some sense? To apply it to some astrophysical ideas. Yes? So there's no noise in the examples I gave. Noise will make things even more complex at some level. But here's there's no noise.
They're essential, because if you're told that each of the points have no noise,
Yes. Very true.
different than telling me that those each have a big error bar.
Exactly.
Do something different. So I think somehow noise seems to be needed in order to answer the question.
Very good point. I actually personally didn't have as much experience with noisy data because so far I've been applying things to mostly not noisy data. They just don't have enough examples. There's a huge, I wish I huge, there's a lack of discussion in the deep learning community about noise because how they determine the noise of a million Facebook pictures. For that particular instance, it is the only realization of it, right? And people don't discuss noise as much, but they are starting to have some new work on noise and error predictions. Famous quote from Yann LeCun that I heard second and third and fourth hand is that if a doctor can tell you your chance of having cancer in 10 years with a rate of 80% success rate, and the machine can tell you about 99%, which one do you want? While the doctor can tell you why, or maybe what the representation is, while the deep learning cannot tell you what, the next question is, the doctor won't be able to give you a percentage of error also. So is the deep learning. Right now, it's not giving you any errors. There's some work called Bayesian neural net. People are starting to look at errors. If you want to take a look at those work. We also had a paper on this on using Bayesian neural net on cosmic microwave background data sets where we actually characterize the noise and compare it to the noise that we know it should be because CMB is the Gaussian field, mostly. So we can actually calculate error very well. So there is some work, but not a lot. The good question about noise. All right. So how do you make generalization of a model better? So this actually hints back to what X talked about earlier about model selection. Back in the days, Ptolemy, astrophysicist, Parsimony, that's what basically people were looking at parsimony, like old days. Occam's razor, among the competing hypotheses that explain observables equally well, we should choose the simplest one. That's sort of the physicist approach at some level. And parsimony is basically, an overset of this Occam razor rule. And there's statistical learning theory, and that people have been doing. This is a long list of work. How do you select model? And there's some important results of statistical learning theory. Is the difference between the training error and the test error is always less than a quantity that grows as the model capacity grows, and decreases as training sample increases. This is kind of convoluted, but basically it proves theoretically machine learning should work given more data sets, and if you have, choices of model capacity. Okay? And this is a plot of model capacity and stuff, and how things are changing when you increase the model capacity. So this is showing the error, the different types of error. Training error, generalization error is just test error. You have this underfitting zone as you increase the capacity, right? And then slowly, when you increase the capacity, think of it, the example of polynomial fitting. If you increase the number, the degree of polynomial, you can actually have decreased the error because you basically fit all of the points. You have all the points, so of course you just fit perfectly. But then the generalization error will increase, and you want to not have this huge gap. So at some point, you need to find, the smallest difference between the two, the training error and the generalization error, and not to underfit and overfit. So this is just restating this. Training error decreases as the model capacity increases, and asymptotes the minimal possible error as the capacity increases. And the test error usually have a U-shaped curve, and people have seen this sort of like canonically. Yes?
Why isn't the area actually the optimal capacity?
Say that again?
Why isn't the optimal capacity actually the big area? Because if we see that the generalization error isn't decreasing already for some time, then it means that the patterns that are learned on the training set maybe still false, but it's just not.
This is a cartoon. I think that's the most important thing. This is a cartoon just to show the proximate behavior. We're not saying that this should be exactly where these two should be exactly close. Yeah, this is mostly a cartoon, but just give you a general trend. It's not from any particular experiment. Non-parametric model. Let's see, what time do we have? We are 1 minute past 12:45. Do you want to keep going?
Please keep going.
Just like a couple more minutes.
Yeah.
The non-parametric model. Yes? Yes?
We have time for sure.
Okay. Non-parametric model. Usually you don't do this because it's impossible to search through infinite possible functions. But there are some examples of non-parametric models, such as nearest neighbor regression. You probably know about this traditional ML method. A lot of us know this. Other possible non-parametric model is wrapping another parametric learning algorithm on top of another model. This is actually not so different when I talked about how this hypernetwork translate multiple languages to multiple languages. You wrap another model on top of another model, that you actually can increase the number of parameters as required by the data. So this idea of wrapping model on top of another model to choose the parameters or number of parameters you need, or to choose the degree of polynomial, is an interesting one that people are starting to work on very recently in deep learning. Errors, errors, errors. I'm not going to go through all these, but since people ask, we did have a slide on this. There will be errors in the data, and there are also error incurred by the oracle that makes the prediction from the true distribution, called a base error. And a lot of these are just talking about what errors that we actually should include when we think about deep learning. There is the oracle, the base error. There's also the noise in the data. And then there's also one more error that I didn't mention, is that when you go from different architecture, like what is the right error? If you use different method, it gives a different answer. What is that error? That's also not included sometimes. And okay. This is a fun one. Yes?
Do they use the term systematic errors, random errors in your field, or you don't distinguish?
I don't use this myself, but I could be wrong. Machine learning has about 300 papers per day in archive. So if someone has used it, I might not have read it, and I'm guilty.
I was just wondering whether they use that concept, because we understand.
Go ahead.
So typically
Go ahead first, and then he can go.
Typically, you will distinguish between what they call epistemic errors
Mhm.
and random errors. So epistemic errors are, it's not systematic, it's what is encoded in the model itself, so the model cannot, it's
And the data error. Yep.
That's the 2 kinds. Yes, thank you. That's
Yep.
helpful.
And there's a question in the back.
Exactly what I was asking.
Yes, I was about to mention one paper. Lawrence Lefasar and Yasha Hasafe has a paper basically all about error.
Epistemic and aleatoric error. Aleatoric is essentially
Aleatoric, yeah, exactly.
astronomy, of course, we have, well, yes, systematic errors in the data. In the data. Of course, there can also be errors also, that obvious. Usually errors in the theory and as well as systematic errors because of the way they set it up. It's not that obvious. Also, error propagation is not that obvious.
Okay, we're coming pretty late. Let me see, how much do we have here? Okay, I can go a bit further, but I think, how's people doing? Can we have 5 more minutes, or should we do tomorrow?
Take 5 minutes. You got us enthralled.
Okay, no free lunch. No free lunch, because it's a perfect title for your lunch.
Then we'll have a free lunch.
So, okay, this is a no free lunch theorem. This is actually kind of interesting, from 1996 by Woppert. Basically, no algorithm is universally better than any other algorithm. That's the rewrite of what they wrote. So this is interesting because basically saying that the best algorithm we can conceive of has universally the same performance average over all possible tasks. So remember that part, as any other one. So the goal of machine learning research is not to find absolute best algorithm. There's no absolute best algorithm. But understand what kind of distribution are relevant to the real world that the AI agent actually experiences, and what kind of algorithm performs better on that particular set of data or that particular data generating distribution. So that's the idea of no free lunch theorem. And so that's why people should not pursue, the best and the newest ideas. I see a lot of astrophysics paper that does, let's just do GAN because GAN is popular today. So I have students who would do that, say, please, 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 let's do a GAN paper. And I'm like, no, because you can't. It's not necessarily the best method. The best method usually depends on the problem, and that's why I think the domain scientists are very important in this field, where you need to tell them, what are the characteristics of the data generation process, that distribution, you have prior knowledge on this, and it helps a lot in selecting the right method. So to give you an example, actually, should I give you an example here? Let me see. We can talk about regularization, but how many people know about regularization already? Oh, wow, that's a lot. So I can probably skip a tiny bit. But the quick thing is, you can change the errors by introducing this extra thing here. They write it in a way so that basically you want to say, I just want to have smallest weight or very heavy weight, right? So if lambda is large, you want, this will be a very strong, basically the absolute magnitude of the weight square. And the excessive lambda, which means you don't want any weight, there's just be underfitting, just a straight line. Approximately correct weight decay will give you, this is called a weight decay, by the way. People give different names to different things. And if you have lambda goes to 0, which means it basically forces it to overfit, for the same example. So you can design your problem in a way by changing the loss function to see what you want to minimize by changing the lambda. That's one of these hyperparameters you will tune with the validation set, usually, or you can basically change the loss function depending on the problem. For example, one of the problems we mentioned earlier, where we predict the 60 phase space information of the particles, when we started using density, it doesn't work. We started density and velocities, we don't have enough space to put everything inside. So in the end, we use displacement fields, mean square error. And it works way better because it can compress information density and velocity all together. And you want to have the best displacement field at the same. So you change your loss according to what your problem is. So that's something to learn. And you regularize it depending on how simple you want, how much weight you want, and how many neurons you want to turn on at some level. More general regularizer. Any modification to a learning algorithm that's intended to reduce its generalization error, but not the training error. That's the definition of regularization. And this is one of the major concerns, basically this or optimization in machine learning. I probably won't go into all the hyperparameters and validation sets, but there's a lot of interesting work that has been going on. If you have not heard of this, Google has come up with something called AutoML that basically tunes and finds the best network on one single problem. That's the claim. But what it actually does is that it tests all kinds of, changes all kinds of hyperparameters, say how many layers, and it's only for residual neural net. All kinds of layers, like how would you design the network, so it's called AutoML. I don't know if the package is out yet. I recently just saw this talk from Jeff Dean. You can Google Jeff Dean's talk on this Data Science Summit if you want to see a talk on this. Bandit optimization, which is Sammy's work. Sammy was one of my ex-students who's now faculty at Washington University. What his thesis was just basically find a way to optimally predict, to find the right hyperparameter set. So training without the graduate student, that's what he called it. That's the real thesis title. So for example, in the polynomial regression, the only hyperparameter is the degree of polynomial, which acts as the capacity hyperparameter. The weight decay parameter is lambda that we just talked about earlier is another hyperparameter that will actually contune. Sometimes a setting is chosen to be a hyperparameter because the algorithm does not learn. It's difficult to optimize. Other times it's inappropriate to learn that hyperparameter on a training set, such as especially those related to model capacity. So back to the regression example, if learning on the training set, the algorithm will always choose to have the maximum possible model capacity, which is the highest number of polynomial, resulting in overfitting. So that's why we want validation set, and that's what people do with validation set. Okay, now that was the part. We have cross-validation. So people know about cross-validation? More or less? No? There's only a few hands, so I'm going to quickly run through it. It's only really useful when a test set's too small. You might not have heard of it because you never have small test sets to establish statistical significance. So what they did is that you're basically repeating training and testing computation on different randomly chosen subsets. So it's kind of like jackknifing it for those who do statistics a long time. They have something called a k-fold cross-validation, but this underestimates the error by a little bit. You can actually derive how it underestimates the error for a very simple process, like a Poisson process, if you want to do that. Quick team question, which we're not going to do because we're running out of time. This is the k-fold cross-validation algorithm, which is fairly simple, but the idea is basically just to split this data set into k mutually exclusive subsets, and then you only do training on some of them and do testing on some other ones. And you keep going for a loop, basically. All right, this is quick now. Why deep learning? This is final couple slides. Traditional methods in ML has not been successful to solve any of the central AI problems before recently. So recognizing images, speech recognition, but mostly what that reason was because of curse of dimensionality. When dimensional problem is high, it's unlikely there's enough data to cover all the configuration possibilities. And we assume something called the manifold hypothesis in deep learning, where most valid data points lie on a small number of manifolds. And that's why we think deep learning will work. And let me tell you a little bit why. This is the reason why original ML works, which is something called local constancy or the smoothness regularization. What it means is that, I'm going to run through quite quickly, is that the function you learn should not change very much within a small region. So this is what the traditional ML assumes. So k nearest neighbor is basically the biggest offender. It will fail to scale to any statistical challenges because if the dimension is really high, you'll have trouble doing k nearest neighbor. Anyone who's done it will probably see it. So the deep learning key insight is that it is possible to represent a large number of regions, say order 2 to the k, by a small number of examples. And that's basically the same idea as you could go into simple, small number of manifolds. So it's not all over the place. So as long as, and the other way to put this is if you introduce dependencies, that's why you use small number of manifolds, between regions with additional assumptions about the underlying data structure, then you can do this manifold hypothesis where things are correlated somehow in these manifolds, multiple manifolds, like this. This is it's not everywhere, so you kind of follow this track. So you can actually do this properly. I was going to run through CNN, but I'm going to stop there because we have lecture notes for this, and I can just say out how to do a simple CNN, which, by the way, this is not even recent, 2016. This residual neural net did a really great job in recognizing persons and common object in context. They were the winning one. The protein folding was interesting if you have never heard of this, where they were the best team while the second best actually got 3 out of 43 correct. They got 43 protein amino acid sets, and you predict the shape, while Google DeepMind actually got 25 out of 43 right. So the best protein folding experts were all very sad if you see like the New York Times article, because the second best was only 3 out of 43.
This is a graph, by the way. It's a graph you identified.
It was graph. But I don't think the code is out yet. So people are always complaining they were not able to reconstruct what DeepMind has done. That was the animation gradient descent method that actually predict the structure of this Cas13 targets. And why shapes of protein is important, because supposing it predicts what the protein actually does. If the protein misshapes, that will get you things like Alzheimer's diseases, Parkinson's, stuff that's not very good. Anyway, so I'm not going to go through the implementation, which I have. And I'll stop for here, and I'll give you one homework problem. Fun part, yes. Just pseudocode. You don't have to write actual code, but if you have not installed any of these Keras or PyTorch or TensorFlow, you should. Google Cloud also gives you credits for like $300 to run initial stuff. So if you don't have any access to GPU, you can also do that. Quick fun questions. Design a CNN to regress from CMB maps to one cosmological parameter. Don't do too many, because otherwise you need a large GPU credits. How many layers do you think you could need? What filter sizes? This is coming from like how we should design your network. So don't write real code, just write pseudocodes. Like how many layers do you think you need? How many, what's the filter size that you think it makes sense? And how many fully connected? Do you batch norm or anything? Just start thinking about those questions without writing any code. And I'm only asking for pseudocode, and we'll hopefully pick, you can work in teams, and we'll probably pick like 1 or 2 teams out to talk about their answer tomorrow. This is very similar in spirits to what we did in ICRR, International Conference for Learning Representation 2018, or what we did for cosmological parameter estimation from large n-body simulations. So that's it for today, and thank you for sticking with me for so long. I know you guys are tired. Thanks. Then it will be free lunch.